Hello Algebra 2 students. This is a video for example 5 for topic 1, lesson 1. Understanding average rate of change over an interval. This is very generic. What is the average rate of change of a function y equals f of x over the interval from a to b? Again, very generic. We don't know what the graph looks like, so they're just throwing in a curve here. They have from a to b, and here's the equation y equals f of x. To find out the average rate of change, we want to understand where the interval starts and ends. So let's say it starts at A and goes to B. Well, the corresponding y value is f of A. So this is the x value. If x is A, then y is going to be f of A. Or if x is B, y is going to be f of B. Again, might be very confusing, but it's going to make sense at the very end. I think you're just going to be able to relate to something you know from Algebra 1. Total change. To find out the average rate of change, we need to know the total change. How much did it change? Well, it changed from this blue point up to this blue point. So, and this blue point is at f of b, the y value when x is b, and this is the y value when x is a. So you can just subtract those two values, f of b minus f of a. That right there is the total change. And we want to compare that to the interval length from a to b. So here it is from a to b. You can just subtract b minus a to get what that interval change is. And this is where I think it will be something familiar to you. To find the average rate of change, it's the ratio of the total change divided by the interval length, f of b minus f of a over b minus a, which you might notice as the slope. It's the slope of the line segment between those 2 points. Doesn't this look like the slope formula? I don't know if I can highlight the whole thing. That makes it a little worse, but doesn't that look like the slope formula? And that's what we have, the y minus y value over the x minus x value. So let's apply that to these three graphs. This is quite a complex problem. We've got three different graphs and we got three different range of values. They want us to look at the average rates of change over the intervals from -2 to 0, from 0 to 3, and from -2 to 3. Okay? All right. Let's see if I can get this all to fit on the same screen. Okay, here's f of x. F of x equals 1, just always equals 1. So when you find the average rate of change from -2 to 0, from -2 to 0, how much did that change? Well, it didn't change. It stayed at 1. And from 0 to 3, it stayed at 1. And from -2 to 3, the whole thing, it stayed at 1. The slope was 0 the whole time. And since let's see if I can scroll down. It has the same rate of change, 0, over every interval. This means it's a constant function. It's a constant function, f of x equals 1. Again, we're trying to find what did the average rate of change over the intervals indicate about the function. Because it was always 0, because the slopes were always 0 for all three intervals, that means it's a constant function. Now, here is a linear function. Let's see what a linear function has for changes in slope. Maybe you already know what the change in slope is. The slope from -2 to 0 was 1/2. From 0 to 3 was 1/2. And therefore, for the whole thing, it was 1/2. It was always 1/2. And since it's always 1/2, this means it's a linear function. So if you ever have that the rate of change is always a certain number and doesn't change, it means it's a linear function. If it's always 0, it means it was a constant function. And then here we have a parabola, a quadratic function. Notice what happens with a quadratic function. The rate of change was -2. From here to here, it's -2. From here to here, it's +3. Here's the math behind it. The first interval was -2. From here to here. From here to here, it's 3. And from the beginning to end, it's +1. All three of those numbers are different. It does not have a constant rate of change over the interval. That means it's a nonlinear function. So in review, If it doesn't have a constant rate of change, it must be a nonlinear function. If it's a constant value, then it's a linear function. And if it's always zero, it's a constant function. Okay, let's take a look at this equation and see what happens to the average rates of change from -2 to 0, from 0 to 3, and then from -2 to 3. And I think, go ahead and click pause, then click play when you're ready to see the answer. I think I have it already typed in. Yes, I do. Now, if it was just y equals absolute value of x, it would come right down through here and right up through there. That's the generic absolute value equation. But because it's a +2, it's actually 2 units higher. Let me change colors for effect because I don't want to have to redraw. There we go. It's the blue function. Y equals the absolute value of x +2 is this one here in blue. Now, what did they want us to do from 0 to, let me look that up. From -2 to 0 and 0 to 3. From -2 to 0, it has a slope of -1. And from 0 to 3, it has a slope of +1. And from -2 to 3, that's kind of weird, it has a slope, I don't know, looks like it has a slope of 1/5 or 1/4. Doesn't really matter. They're all different numbers. -1, 1, and the 1/4 are all different numbers. So what we can say is what we said on the previous problem, that it's a nonlinear function. This y equals absolute value of x +2 is a nonlinear function. Let's see what they wrote. The rate of change changes over the 3 intervals. Therefore, y equals absolute value of x +2 is a nonlinear function. That's all we have to do. This is the last example, so let me go over the concept summary before I tell you the problems that you can do. If you don't mind, this might be worth a screenshot or two. I know it's a video, so you can replay it. Unfortunately, I can't really fit. Yeah, I can. Some key functions with key features. There we go. If it's a linear function, that's the graph. The key features, domain is all reals, and so is the range. And it's increasing because this is a positive function. If it was a negative function, it would be increasing for the whole interval. The intercepts, this has an intercept of x-intercept of 0 and a y-intercept of 0. That's not true about all linear functions, right? If this line were over here, it'd have different x-intercepts and y-intercepts, and if it was going down, it'd be decreasing. So I'm not so crazy about memorizing that. It's just an example. Here's an example of a quadratic function. It's either going to open up or open down. It's going to have a vertex, which will be a maximum or a minimum. It has an axis of symmetry, which you can find at x equal -b over 2a. Here's the domain and the range. Remember the range, if it opens up, it has a minimum value, and if it opened down, it would have a maximum value, so it would be just the opposite, written in the opposite way. An absolute value function is going to look like this, but that's not always true. We had one earlier. You can go back to an earlier video. I forget which one it was that had it was a minus the absolute value of x, and it opened down. So even though this is a nice summary, it isn't very vague. It's specific to these 3 equations. You just want to recall the videos that we had before. Let's see if there's another. I don't think there's another concept. Nope. Okay, so going to the problems that you should be able to do after this last example, you should be able to do problems 22, 27 through 30, and 33. That's it for this video. Have a great day.